there's lots of food left.
Guess what? I've got the PC connection wrong.
Really? How did you do it?
Just pop up, just restarted everything.
Ah.
We right up against the wire, we weren't taking it to. It says there's some food out there.
There's loads of food out there.
Right, I'm going to grab some.
Now's the time.
Yeah.
Yeah, it's empty now. So many mini things.
Thanks very much. How's it going? Okay.
Watch out for the wires.
Yeah. When I saw those queues, I thought we'll never get food.
No, there's still loads left.
Mm. When you copied the cards, you put each card into its own folder.
Yeah. It's not just a potluck folder.
Can you just check the feeds coming through from the laptop?
Yeah.
Okay.
I get a couple more sandwiches.
More sandwiches, fresh air.
need to interrupt the lunch.
We do the live cast with video. With the setup here, you have a HDMI socket there, and I think,
mine doesn't have a mini.
in which case I think you might need a converter.
I think that's what I'm...
That's what you need. A thunder.
I think this is fine.
Well, yeah. And my tip on this is don't get too close to it, because there's nobody adjusting volumes.
Right.
And it can sometimes get to distortion.
So let me take a look.
Also, just another thing that we found is the Wi-Fi code is a one-time use. You
Yeah.
can't use it again.
Oh, is that right?
So grab yourself a few if you need to go offline. You lose the connection and you can't get back in.
Oh, that's a good point, because I did mean to possibly demo something online. So
What I would do is get your internet connection going, turn off the PC closing itself down, keep the connection live.
right,
and then
okay.
you'll be fine.
Well, we just need it in the next 5 minutes, I guess, or so. So I'll try to do that right now.
Video connection, see if you can get up onto the...
Yeah, I think that's probably the key. Sorry, let me just see here for a second. Which one is it? So I guess this is the HDMI, and the HDMI that I have is I saw it somewhere. Right, so it's this teeny weeny little thing. No, that's not it. Do you know if there is a VGA? Because there is a VGA here. On the other side. Kind of the glass.
They've only set up... yeah. You're going to need some help from the technicians.
It's okay.
try and do this over on technical issue. I'll try to get the guys to the office is not nearly there. Right, I've run 200 metre dash. The IT department is shut nobody there. No problem. A lot of working porters on the desk. So
That's okay, no problem. I believe that there is a sort of a backup that I sent them the slides, so I just updated it on Dropbox as well.
okay.
So basically, an alternative computer or whatever.
Do you want me to give you an alternative computer?
No. Actually, you know what? No, I'm going to run upstairs and talk to the.
Lending him one of our laptops.
Okay, isn't that mine? Are you okay with that?
Whatever. No, I mean, whatever's quick. We just need to get a new internet code.
Okay, easy. I'll get that for you now.
So, we can transfer. You've got the USB stick to transfer.
That might be a little bit hard.
There should be enough battery power for a little while.
That's fine, as long as it doesn't turn off. I mean, it only needs to go for half an hour.
Yeah.
Do you think it would last?
I should say so. You can tell if you check on the battery.
Just make sure that this is.
Yeah, it's on 100% at the moment.
Oh, hey.
Hi.
Yeah, just if you had a VGA that could plug into this.
We've set everything up with HDMI.
You see, it has this mini HDMI. What is it? This one, or a VGA, which is the big one.
It's all. I think we'll just go with transferring it because we know this works.
With that one or whatever works.
This is a spare laptop that we would be using as an emergency anyway, so this is fine. We know this works, so yeah. We just need another power socket. We've run out of power sockets for this.
I have.
Not VGA. We're okay. We'll just use this one.
Or maybe that, but.
Not for the security though.
Yeah.
Okay, so you just need the internet connection.
Yep. Is the Wi-Fi code for you?
Okay, I'll just do that. You can tap it in.
Thanks for speaking up.
Hey, that's all right. We're kind of learning how the place works. There you go. And then, sorry, your name is?
Max.
Max. Yeah. So if you just transfer your presentation onto the, then we're good. Is it PDF or PPT?
Yeah, it's a PDF.
PDF. Ems?
Yeah.
You set up a PDF player, didn't you, on here?
There's Acrobat.
Did you?
Adobe Acrobat's on it.
Yeah.
And Media Encoder's on there as well at the last resort.
Oh no. Leave that.
Is the PC feed coming through, Ems?
Brilliant. Let's save it there. And would you like to lose the lecture? Yes, okay, perfect.
Okay. We now need.
Just copy this over, sorry.
Yeah.
For a sec. Here. Do you know where the USB here is? It's probably on the. Do you see it's on this side? Oh no, that's. Thanks so much. Just give me a sec. Hopefully that should find it. Nope. And that's the presentation, Cambridge AI.
Okay.
Just double click that.
Sorry.
No problem.
Maybe after
We might need to copy it onto your desktop as we can't.
Yeah, that's a good idea. Oh, I see. It's not.
It's not coming up.
We can try my laptop as well.
Okay.
Okay, take this out.
Yeah. Okay. So, try that. Okay. This was working earlier.
You need one of these. Yeah?
Okay. Cool.
Yeah, it's coming through. I'm going to set this.
Okay, so I will go outside and let the people in.
Wonderful.
Do you need any water?
Hey, nice to meet you.
You?
Yes.
No, yeah, sorry.
Where are you from?
I'm from Cambridge Park, so I'm just going to be introducing you.
Okay, what about the region?
Oh, I'm sorry, Serbia.
Serbia,
Yeah.
yes.
Oh no, do you know what? I remember looking at your Twitter,
Yeah.
and I said to my mum, like, oh, it's Serbia too. Sorry. Yeah.
So I have 25 minutes?
I think so, yeah. I think so.
Just
Half an-
yeah. And I'll just give you a 5-minute cue in the front, just when you're like, I'm a bit fine.
Wonderful, thank you.
Yeah, I'm one of the first gen to be born in England. It's like my family all from Serbia. So. Yeah, so my Serbian's like half-half, like not that great, but
It's okay, yeah.
it'd be really good to catch up after as well, because I'm trying to pull together some content for basically for aspiring data scientists to how to get into data science roles and interview techniques and stuff like that, and just tips as well. Would be really good as well.
Yeah, no, sounds great.
Yeah,
Yeah.
thank
So what is it that you do? Are you a data scientist yourself?
Oh no, I do marketing, so for Cambridge Park, yeah. Yeah, but it's like my first piece. I think everyone's in. Cool. So welcome back. Hope everyone's now feeling more refreshed and invigorated. We're now going to welcome Dr. Maxim Sipos from Casual Lens, who will be talking about automated feature extraction and selection for challenging time series prediction problems. Sorry. So yeah, give everyone.
Thanks very much. To explain the name, it's actually pronounced causal lens. And I'll tell you in a little bit why we named the company like that. So we are in the field of trying to understand time series data. And so as a first step, I'm going to tell you a little bit about what time series are. And really, time series are just measurements of some variable over some time, right? So in effect, anything that you measure has a timestamp associated with it, right? It's the time when you measured it, right? Unless you're in a physics experiment or a chemistry experiment and you control all the little things, you will always have some measure of a circumstance in which you took some data point and the time when you took it, right? So in effect, everything is a time series, and the time series data is exploding. You've got everything from health data to location data to data inside data centers, measures of load and log and security. You've got obviously financial data, which has been using and collecting time series for a very long time, economics as well, and of course the IoT, Internet of Things. All of these things are generating loads of data, and the world is only becoming more and more driven by all these time series that are being generated. And so that's what time series are. They are numbers associated with time, or they could be categories associated with time. You could say, is it sunny, is it cloudy, is it rainy? Okay, so now we deal with some of the most challenging time series problems in the world. Here is how a time series problem looks like. The green bold time series there is a time series that we are interested in. That could be a measure that we would like to predict in the future, and we want to build a model to predict it. And maybe we have some input variables. Those are the blue and the red here. Those are the variables that we want to use to make this prediction, right? So what is an example of something like this? What would we like to predict? We would be interested in predicting, let's say, a stock price in the future, because we might be interested to make a trade and to buy that stock and profit from that. Or we might be interested in, maybe we are selling some sort of a service and we want to predict what will be the demand for this service in the future. And what we know, for example, as an input variable, is how much money we're spending on marketing, right? So then the question becomes, can I use my marketing spend to help predict the demand or the sales that I'll be making? So the reason I'm calling these problems challenging is because they have a lot of properties that make them really hard. First one is that they're relatively small data. It's hard to collect loads of time series data. And some of the most interesting time series data sets that we have historically are really, really small in quantity. Some of the most interesting macroeconomic data comes out quarterly or even annually. So the data is small. Moreover, it's non-stationary. Non-stationary basically means that the models that these time series, the behavior of these time series is changing over time. It's non-stationary. It's essentially dynamic, right? So, if we build a model today and we put it in production, 6 months from today, it might not work anymore. Because, in this world, we would say basically the world has changed. The model has stayed the same, but the world underneath it has changed. And so now this time series is behaving in a different way. That's what it means to be non-stationary. The data is also very noisy because these measures come from all sorts of sources that could be noisy. We use this parlance of sort of time series literature where we call about signal. We talk about signal. So these data have very small signal. In effect, the noise is just high enough that to be able to predict something, it's very hard because the signal in the inputs is very low. And there's a few reasons for that, and we can go into them in more detail. So how would you go about solving this problem? Where do you even begin? There's actually a number of things you could do. You could go back to econometrics in economics literature, going back to the 30s. You could look at what people in the signals processing world have been doing. Physicists have been interested in this problem for a very long time. And obviously, you can also apply machine learning to it. So what would the machine learning model look like? To first order, it's not that hard to set it up. You essentially, let's look at the bold green time series in the middle. You want to predict it in the future. So that's the two little circles. That represents a point in the future. That's the dotted line represents some point in time. So some point before that, you've got a measurement. You only know what's happening on the left side of that line, right? But what you're interested in is predicting what's going to, where is the green line going to be at that double circle point. So one way to do that would be to just take those 3 points that I labeled with circles and let's say make some sort of a regression of those 3 variables against the fourth one. And then you would have some sort of a sliding window where you would go across this and you would build up a sort of a regression problem to solve that. And if you try doing that, you will find that it doesn't perform very well. It doesn't perform very well for a couple of reasons. It doesn't actually extract all the information from these time series. And quite often it won't work at all because maybe the values in these time series are not what is actually driving this variable in the future. Maybe it is some measure that is somehow associated to the values. For example, the momentum of these time series. So maybe what is driving, so let's take an example. What's driving our sales, maybe it's not the amount that we spend on marketing, but how we are, what is the momentum that we have in increasing our marketing spend, for example. Or maybe the stock price is actually driven by the change in sentiment, in Twitter sentiment, and not in the absolute value of what the Twitter sentiment is today. So that's one example for why this kind of a regression problem wouldn't work very well. And we provide a solution for this. And the way we do it is hard, but it's doable. And there is no single individual technique that just solves it out of the box. So we don't come with deep learning and we just say, here we throw it into a deep learning network and we get a solution. We don't go back to econometrics because that doesn't perform as well either. Essentially, we built a way to optimize across all the parameter space and all the techniques and technologies out there and build an optimal solution by connecting pieces of the models together automatically so that what we end up with is what we call an optimal model, because really it's a model that's extracting all the possible signals from the input variables. That's the idea. So we do that in a couple of ways. We expose a way for humans to interact with the machine in the process. So we give essentially a way for a human to put a prior and to say, I believe that these variables should drive this model. So it's a way for a human to nicely interact with the machine. We figure out how to impute and align the data in the time series world. We extract all these time series components that I talked about, things like momentum, how are the time series changing. There's a lot more of those as well. We select which of those features actually matter. We select the algorithms, the hyperparameters, and we optimize the whole thing. I'll show you a few plots just to kind of get you an idea that does work. When we did this analysis, we applied it to a number of data sets and metrics, and we tried to vary one step in that pipeline at a time. And so one covariate at a time, we try to see, does it help or not, right? So for example, this is the process of letting a human put a sort of a prior on features in the model. And if you measure it as a function of the score, or as a function of the absolute error, or as a function of Pearson R, or some variable like that, you will find that in general, with various different data sets, this process helps and is actually improving the model. If you do feature extraction, or if you don't do feature extraction, you can compare those two and you can find that, well, actually, feature extraction helps a lot. The same is with feature set selection. So, in effect, I showed you 3 of those examples. Those are just some basic experiments that we did where we saw that each of those components helps build better models. But how do we put it all together? That's one question. And in fact, this is really interesting. The sort of classic way a physicist or a machine learning person would approach this is through some sort of a derivative-free optimization. Why is it a derivative-free optimization? It's derivative-free because you're in this really weird hyperparameter space where you are actually optimizing across model architectures, right? So if you think about it, what would it mean to have a derivative, some kind of a difference between a lasso and model and a gradient boosted tree, right? That doesn't make a lot of sense, right? So this is why you're actually kind of in this space that is sort of a Cartesian sum of multiple spaces, and so you can't really have any reasonable notion of derivative. So what you do is you use something that's derivative free, and some examples of algorithms like that are genetic algorithms that you could use. You could do Bayesian optimization as well, or things of that sort. So that's how to first order, that's how we solve the problem. And when you do that, you also see if you do a kind of a full pipeline optimization, you outperform just optimizing each piece of the pipeline. So you could optimize each piece of the pipeline individually, but you could then do, or you could do the holistic thing. If you do the whole thing together, you get more performance as well. So there's quite a few steps, and at the end of this whole process, you built a model pretty much automatically, and that model is close to the best you could do. And now, so what we built is this machine that can generate automatically these models that automatically extract signal from the input data and produce a prediction on the time series. Now that we have that, I think this is a really powerful abstraction. And with the right set of data and right organization, you can now start having these models. You can start building these predictive models internally within your organization. You can kind of start producing these models that are predicting the world, and you can start connecting them together. And in this way, you are sort of building a model of the world. You're understanding the world by using these little bricks that you're connecting, and these bricks are the technology that I just showed you. What is nice about it is that you've got the technology to extract all the signal from the data. So what you then focus on is, well, what data should actually flow in, and how do I model the world? And that's actually the really exciting question as a data scientist. It's not about the nitty-gritty and the derivative-free optimization, right? What's really exciting is, trying to understand and build a model for the whole world. And of course, there is a question that one would like to answer by building this sort of a world. The reason why I have a grail there is because it's a very hard question. It's a kind of a holy grail. It's about understanding what is the reason that things happen in the world, and what causes, what is a cause and what is an effect. The way to do it is if you have a predictive model that predicts something, there's this notion of Granger causality. The idea is if something predicts something else, that means that in some sense, it causes it, right? So it is a sort of a proxy for causation. And that's the reason we named the company Causalence. I do want to mention very briefly about AutoML. We actually heard from Google today about it, so that's really great. We also, so I mentioned that we apply derivative-free optimization. This is about AlphaGo 0. we also do a sort of an AutoML type of approach to go beyond derivative-free optimization. And so the idea there is that you should be able to build a machine that can be smarter than a derivative-free optimization, okay? A derivative-free optimization, in effect, or let's say Bayesian optimization, in effect, it doesn't have the ability to perform actions on the problems that it's trying to optimize, right? It basically has parameters it's able to tune, and that's all it can do. We've set up this approach where we've got our machine interacting with the true model. We can actually generate data, artificial data, kind of like how AlphaGo Zero plays games against itself. We can generate, let's say, fake economic data that has some sort of underlying economic model that we know, but we don't tell the machine what that model is. The machine can perform these experiments, and it can learn how to build a proposed model, the best model it can possibly build. And then we can obviously score that because we know what the real model is. The machine doesn't, but we can see how well the machine, what experiments did the machine take to figure out that model, and how good was the end result. And we limit the computational budget of that machine because we obviously want to figure out that answer in a finite amount of time. And so this is how we end up setting up a game, in effect, that can solve this problem. And this approach actually does outperform the sort of naive Bayesian optimization you could also do. There's other stuff as well that you can do using this technology. You can look at across huge cross sections of data, doing also, looking at thousands of time series at the same time and understanding how they all behave together. It's a very interesting problem also of integrating data at different frequencies, and obviously how do you apply deep learning to time series, and how do you express time series models in tensors. And we can talk about that as well. Please feel free to come and ask any questions. So what I just showed you is how we built one of these bricks, one of these little components in this system. But really what we are excited about is the ability to start using these bricks to build up a model of the world, right? If the only way to do that process effectively is by building an abstraction layer, right? Something that lets you build these bricks and connect them. These boxes, you need to be sure that they are correct and that they are actually extremely scalable. I didn't mention anything about it, but the boxes that we end up building are very transparent. They actually explain to you everything that they are doing, and they're trying the system is trying to build these models in a very human way. And this is very important. If you're trying to model something in the real world, you really want it to be something that's reasonable and that you can understand. Otherwise, people won't believe you, or there is a really serious danger of overfitting, right? And building a model that's too complex and doesn't generalize very well. So I can just very briefly show you a little demo of the technology. So I'll just click here. And it's kind of very similar to the demo that Google has shown as well. Once you have a data set of time series, and once you enter it into the platform, you get what looks essentially just like a usual experiment that a data scientist would set up. So it involves a period where you're training your models, the history, a period where you're validating them, and then what you get is testing as well. And this is just a small UI we've built. But basically, with one click of a button, you can build a model that actually just is as parsimonious as possible. And I'll show you how one of those models looks like. It's a very basic one, but if we click on an old one, because I don't want to wait for it. Yeah, so you can actually zoom in and kind of get the idea for how well this model is performing out of sample, and you can see it point by point. And then you can actually dig through all the little details of what went into that model, how important were the features, what were the responses of the features, and so on and so forth. So, you know, you can evaluate all the performance metrics of that. And in this way, what you've got is essentially a framework to build on top of which to build a whole network of models. So we're based in London. We are relatively early stage and you know, an exciting place to work. We are hiring at least 2 data scientists in the near right now. So please feel free to talk to me about that as well. Any questions? No, that's exactly what we do. Yeah, I mean, autoregressive models are a part of the system, and autoregressive features do go into the calculation. And so, what you just mentioned about Granger causality, that's really the idea. In effect, if you have a model without some variable, and it's 75% accurate, and then you add another variable, and all of a sudden it's 90% accurate. You could argue that that variable is effectively Granger causal, right? And like you said, yes, the autoregressive models and the errors that happen during the process and all that stuff is a part of the model. A model can be actually seen in time series world. A model is a bit of a funky thing because it is almost like a strategy, right? That's evolving over time. It's not a linear. It's not just a pure function. Any other questions? Yeah.
Do you have a notion of meta-causality, which is more than just like a Markovian causality, where you know, you're in time series over time, but something maybe aren't just like cause and effect without memory, memory causal?
Right. Yeah, that's a really interesting question. I mean, I'll tell you some aspects of time series are interesting when it comes to non-stationarity. So you do see things where some variables really drive certain, you know, act as really good predictors for a while, and then they stop being predictors, you know. You can think about it as sort of what is important at this time. Maybe you know, maybe if there is some kind of a big news outbreak, then all of a sudden sentiment is really driving a lot of things because everybody's reading about it, but then at one point it stops being the case, right? Now, meta-causality, I guess, I mean, there is some literature in the world about how do you build these networks of causal models, and in effect, you're never really sure if something is causal or are the two things potentially being caused by something else that's almost like a third factor that is causing both of them, right? So some of those questions you might never be able to answer from data alone. Thank you.
Get it on the screen. That's good. Try that.
Come on, where are you? There it is. There it is.
That's gone.
Come back. Okay, good. That's definitely better. Great. So once again, thank you to Maxim from Cause the Lens, sorry, who are also one of our data science bootcamp project partners. So now I'd like to welcome Dr. Jeremy Bradley from the Royal Mail, who will be doing a talk on data science as a transformative process. Sorry.
Thank you very much. Okay. Well, thank you for staying on for this. And I guess you might be wondering, what is Royal Mail doing here? We're not exactly a tech startup. We're not exactly sort of 10 years old or 5 years old and thinking, how can we do cool stuff with neural networks? But I'm hoping to show you today that quite a lot of the things you've been listening to are extremely relevant to a more traditional industry, shall we say, and one that is looking to progress and go forward in this area. I'm Jeremy Bradley. I'm actually an academic by training. I'm a computer scientist, and I decided a few years ago to move into industry and to see whether we could make that final jump from technology and concept to actually delivery. And what I hope to show you today is two things. Firstly, some of the strategy that we're trying to run in the group from a fairly sort of high level, how we're trying to achieve some interesting transformations in, as you say, what is rather a traditional postal delivery industry. And also I just want to show you a little bit of sort of technical detail on some of a couple of the projects we've got running, and some of the challenges that then hits us when we try and interface that to a company which wasn't set up with a web page and a box saying, I feel lucky, or anything like that. Okay. No, that's not a very good thing, by the way. So, if the problem was to deliver a letter from here to Bristol, then that's not a hard problem. And even if the problem is to deliver a sack full of letters from here to Bristol, that's still not a hard problem. Even if it's 20 tons of letters, you know, eventually you hire enough vans or you hire a couple of articulated lorries and you do that. So that in itself is not a problem. So what I want to do is give you just a very, very sort of broad flavor of what the problem is. The problem is this. It's not 1 or 2 letters, it's 50 million letters every day, and it's going to 24 million addresses 6 days a week. So, you know, they actually do get Sunday off, it's nice. 115,000 post boxes, not to mention all the businesses we do direct collection from. And that goes to 1,250 delivery offices, which you may be familiar with if you've ever had to pick up a parcel that you weren't in for. I'm very sorry. And we have, I know you do get some interesting comments. All right, so, and you have little or no notice, or we do have little or no notice of those letters. You know, for a lot of those, they just go into the post box. And we have a commitment. It's a regulatory commitment to deliver first-class post to most of the UK within 24 hours, usually within 12. It can be posted at 5 o'clock in Penzance and arrive in Aberdeen at 8 a.m. the following morning. Or with second class, 2 to 3 days. So, marvelous. Ooh, that's interesting. What are you doing? Come back. Good. So that's the problem. So it's essentially managing a very slow IP network, but ones where the the packets, if you like, are rather large articulated lorries or vans, or indeed people carrying your post to your address. So it's complicated in the sense that it involves a lot of people. Nearly 200,000 people, in fact, manage the Royal Mail postal network. And they make decisions every day which impact in a good way, most of the time, sometimes maybe not such a good way, impact the operation and define whether we are successful or not successful in delivering what we need to deliver. And we like to think it's complicated, and certainly if you thought that if you think of the company as being the combination of 200,000 people's decisions in executing what the company does, and that was somehow the state that you would have to represent, then my goodness me, that would be a very, very complicated system. But being a computer scientist and someone anyway who abhors complexity, I like to try to make things as simple as possible, at least until I know that it's not as simple as I thought it was, and I ought to be putting a bit more time into working out a slightly more interesting and maybe more complex process. So let's start simple. And so the challenge we set ourselves, we're a data science group in the heart of this traditional company. We only started doing this about 18 months ago. We're essentially a sort of startup within a large company. And that's really the only way you can try and sort of couch yourself to succeed in such an environment, because otherwise it just overwhelms you. What we'd like to do is imagine that we could redesign the whole company. You know, let's start over. Let's see what could we do. How would we run this if we just started again tomorrow? So could we redesign the company around notions of data science, algorithms in AI, and decision science? And as a few of the speakers have alluded to today, you know, there are so many cool techniques out there, so many really exciting approaches that you could use. And oh my goodness, I mean, when I was lecturing computer science, it was true then, and it's just as true, if not more true today, you have to be so on the ball to know which of those techniques you should be selecting. Which from your toolbox should you be taking out of your bag to go, I'm going to try these three, and we're going to do a little race test with all of those, and then we'll see which ones go out. You can easily get lost in this particular forest, random or otherwise. So that's the challenge we set ourselves. And it sort of guides what we're trying to do. We have to do lots of miniature projects along the way to get ourselves there, but that's what we're about. Let's see if I can make this full screen again. No, it doesn't want to. Marvelous. Okay. So the first thing we need, rather happily after Maxime's excellent talk, is a really good forecast. And forecasts are the lifeblood, especially of an operational company, a company which depends rather a lot on the demand for its service. If people stop posting letters and parcels tomorrow, Royal Mail would just be sitting there drumming its fingers waiting for the next one. So, you know, we really do need a good forecast of economic activity, customer behavior, all of the businesses, quite a lot of tech businesses that feed into our network, in order to anticipate how we can move our resources around in order to service that demand and get letters there the next day. I said we have little or no notice. Yeah, we have. Let me be a bit more specific. Yes, if you post a letter, we're not going to know about that. Not unless you've pre-bought some kind of tracked letter, but that's fairly unusual. If you're a business and you're talking to us and you're posting quite a lot of letters or parcels, then you might give us something called pre-advice. Pre-advice is where you say, I've got 5,000 packages, they're all about this weight, they're all about this size, and they're going to these 5,000 different locations, and you're going to get them in about 12 hours' time, and we'll deliver them directly into your warehouse, inject them into your network. So that's great, except it turns out they don't tell the truth all the time. And so they lie about the size and the weight and sometimes the number and sometimes where they're going. I mean, how they expect them to actually get there, I have no idea, but anyway. So there's quite a lot of resources we need to move around, and we've obviously got this quite noisy data set that acts as a partial input into what we do. We've got the largest van fleet in Europe, which is has its upsides and downsides. 150,000 postmen and women, and who walk out in all weathers doing the most amazing on-the-spot optimization. Really very impressive. So let's be really simplistic about this. I said I wanted to start simple. Let's imagine a company, doesn't have to be the Royal Mail, but as a function. What does it do? What are its inputs? What are its outputs? And let's start from there, and let's then try to sort of scale it up and add a little bit of more color to that. So to start with, we're going to have a commercial forecast, a time series forecast, almost certainly. We're going to have customer data of the pre-advice I was telling you about. No matter how good or bad it is, it's still an input. We've got competitor information, lots of information about initiatives, marketing strategies, and marketing initiatives that our competitors are doing. Weather forecasts, big deal if you're delivering stuff on a road network, which might not be fully open, or might be rather slick or something like that. And just general traffic information. We're working very closely with Highways England, who are themselves going through a transformative process of closing most of the motorways in the country overnight for the next 15 years. So a lot of inputs come in, and somehow we've got to transform that into outputs along the lines of resource configuration within the company. We want to actually deliver the stuff, so that's a pretty major output. And ideally, I say CO2, it could be anything, in terms of we want it to be as sustainable and environmentally unimpactful as possible, just so that we can keep on running the economy and helping the company sustain itself into the future. So let's just sort of flesh that out a little bit. It's not as simple as that. It's not as simple as this either, but so we'll start with the inputs in the top right, top left-hand corner, and the forecasts and customer data come in. Then the company function itself is going to, the act of executing the company's function will in itself modify the forecast and modify how our customers talk to us. If we do a good job, our customers will change their behavior and maybe feed us more parcels and stuff. If we do a poor job, then they maybe give us less. So, it's not, our process will impact how other people behave. There is a game theoretic element to this, for sure. The resource configuration is much more of an internal transition. It's much more of an event which happens as a result, as a reaction to all of these inputs, and allows us to put our vans in the right places, our people in the right places, all of that sort of thing. And then the outputs we can think of as being a bit more than just delivering the parcels, though that is obviously really important, but also, we want to be able to predict the delivery windows of these packages with increasingly narrow windows of delivery. We want to provide tracking data to individuals, and again, we want to have as low an environmental impact as possible, and lots of other things I'm sure you could think of as well. But whatever you think about this sort of function, this sort of very, very hairy box that does all of these things, it's got to have certain properties that are really, really important to enable it to be useful and acceptable within a company environment. So first up, there are different windows of time at which you could execute this function to be useful. So a company would like to know not just how many vans should I have at this location tomorrow, or indeed today. When should I be sending these vans out? When should I be sending these people out onto to their delivery patterns? What route should they be taking? These are all the sort of key operational decisions that you want them to be able to inform and make decisions about right now. But you also want to know where's the parcel delivery market going in a year's time, 2 years' time, 5 years' time, 10 years' time, because I want to buy the resources or lease the resources that I'm going to make my deliveries in 5 and 10 years' time. I might want to have a plan for that now, or at least want to be able to put together in the next few years. So I've got to have a strategic view of this function. So I need to be able to run this function over very differing time windows, which means that my dependency on my forecast is going to be very different. I'm going to need a forecast which is capable of good short-term predictive capability. I'm going to need a forecast which is going to have a robust-ish long-term view of market conditions and demand conditions over a much longer time. And that's a very challenging thing to be able to do, but it's going to need to be done because that's exactly what the sort of company would expect to be able to do to make the decisions it needs to make. It needs to be able to cope with levels of uncertainty. All the things, almost anyway, that I've seen today and you've seen today, all of the amazing techniques you've seen, very few of them come up with it's definitely a cat, or it's definitely a dog. With 100% certainty, there is just that 1.2% certainty that it was a muffin, or whatever. Yeah. And therein lies the challenge. All of the things that you're going to put into this function, and most of the things you're going to get out of the function are going to themselves have probabilistic behavior associated with them, or probabilistic weights associated with them. And you've got to be able to cope with that, either in the sense that you have to be able to consume something which has a distribution or has a probability associated with it, or when you produce your configuration, your resource configuration, the business, or maybe yourself, depending on who's making the decision on that data, has to be able to know what the thresholds are. If you're only 40% sure that you need an extra van at that location, well, do you put the van in that location or don't you? I mean, that's a deterministic thing, and you're only giving a 40% certainty to it. So what do you do? What's your threshold? What's the risk if you don't? What's the waste in cost if you do? And so on. So you've got to be able to cope with that. And yeah, as it says at the bottom, one of the things you'll do if you work in data science now, or if you go on to work in data science in the future, one of the best things you can do when you're running these algorithms, when you're running these approaches, is to be able to give the people who are consuming it an idea of the risk they are taking by acting or not acting on this analysis. And it's very easy to walk into a commercial environment where the process is all set up on I just want a yes or no, and your algorithm is saying 80-20, something like that. And to be able to have to explain, often the company is not configured to accept a probabilistic answer. It's configured to accept a yes-no answer. It's not configured to accept a probabilistic answer. So being able to show the company where the risk lies, where the probabilities lies, what the implications of those probabilities are. So, giving a mean is not often the best solution. Often you will find yourselves giving a conservative version of the truth, say, because you understand that if you err one way, if you give if you say it's a dog when it was a muffin or something, to put it crudely. So then you will incur some higher level of risk if you say that if you say that the articulated lorry should be in Warwick and not in Birmingham, then you incur a much higher level of risk in terms of the cost that delivers, or might cost the business, than if we just had two articulated lorries. Although that in turn has a cost associated with it. So you've got to take that into account, and you've got to be able to explain that to the people who are consuming what you're producing. Okay. Goodness, right, so I want to do this very quickly, and then I'll show a quick demo, and then we'll be done. Okay, so I just want to give you a flavor for what the Royal Mail network looks like. It's quite simple, and then, funnily enough, human beings are fantastic at making things very complicated. Right, so you post a letter in Southampton, and it goes into a post box. The postman comes round, or postman comes round in their van, empties the post box at about 3 o'clock, 4 o'clock in the afternoon, takes it to a delivery office, and that's what the DO stands for. There's nearly 1,300 of those around the country. Then a lorry will come to your local delivery office and several other delivery offices, pick up all of the post that's been collected from post boxes and businesses around the country and take them to mail centres, which is what the MC stands for. So these are essentially just sort of big aggregating factories that take in the parcels, the letters that you post, and push them down the network. So at about the middle of this, there are things called regional distribution centres, which are nothing more than what are called cross-docking locations, where you take a big set of cages from all over the country, cages with bags of post in, and you say, these cages I'm going to put over there because they're going to Manchester, these cages I'm going to put over there because they're going to Edinburgh, and then you put those all onto lorries, and then off they go to the outbound mail centres, which are these red dots, which are about 40 mail centres around the country, and then they, in turn, push them out about 4 o'clock, 5 o'clock in the morning to their delivery offices for the deliveries to begin from about 6 a.m. through till 1 o'clock or so. So that's how it all works. And as I said, I'd like to start simple with something like this. This feels like a very nice feed-forward flow network to me. So let's just start with something like that. For the one or two people who are lucky to have me lecture to them at Imperial, I used to do things in queuing theory, so funnily enough, we deploy a queuing theory model to do this. And we put in anticipated post volumes into our DOs from forecasts that we run as a group, and we look at routing probabilities from DOs to mail centres to distribution centres to mail centres and back out again. And we apply very simple formulae in the sort of, if you've heard of Little's Law and that sort of thing, to look at what are the storage requirements going to be at these locations, which locations are going to be stressed in terms of going to receive more post than they're used to, what's the implication then for how many people should be on shift, how many vans might they need, what are the size of the vans they might need to actually service that requirement on a daily basis. And yeah, it's a very interesting model. We've got some good collaborations with the CormSys, CDT, and University of Southampton working on that now, and we hope to put something live going on that in the next few months. So along the way, as you're putting this sort of grand thing into place, you end up in a position where you're controlling your resource in some way, and that has certain complications and implications. So one of the resources we're asked to control is the van fleet, of which I said we have quite a large number of them. It's an enormous beast. It consumes 200 million litres of diesel a year, which is not a very happy fact, frankly, but there we go. It operates out of these depots, and the question we're asked is, in one of these projects, is how many should we have at our depot locations? Ideally, we'd like to have fewer. And the way the company has operated in the past is to sort of ring up the delivery operation, the depot manager, and say, you've got 100 vans, I'm taking away 5 of them, make it happen. And that has problems, because what that does, they're used to running their operation with 100 vans. They might not be running it desperately efficiently, but they're used to doing it. And in fact, they've probably used up any slack that they may have had doing other useful, maybe look-ahead activities that they haven't told you about with their 100 vans. You then come along and say, I'm taking 10 vans away, and just saying, now do the same thing you were doing before. Everything else must stay the same, but those 10 vans are gone, you've only got 90 vans. And you give them no tools by which to help them solve what is an optimization and planning problem, and quite a hard one when you're dealing with 100 people that are also having to turn up and drive those vans at the same time. Then you introduce a lot of stress and a lot of unhappiness into the operation. And so one of the things we're really, really trying hard to do is to try and give parts of the business that are very stressed and rather unhappy because they have no tools, the tools to make them able to do the job they can do with the resources that the company is able to afford, essentially making it the company's problem. If the company cannot solve the problem of how to deliver post with 90 vans, then it shouldn't be trying to give it to someone who also is struggling to deliver the post with only 90 vans. And reasonably so, if the tool can't do it, then the manager is allowed to come back to us and say, well, why isn't your tool better? Why can't you sort us out? So we wrote them a tool. It doesn't look like this as far as the manager is concerned, but it looks like this behind the scenes. Let me just run it quickly. Okay, live demo is always fun. Let's see if this works. Oh, no, it doesn't. Yes, it does. Good. All right. Sorry. Oh, I do apologize. That's terribly flickery. Sorry. I do apologize if that's giving you a headache. I will try not to have it keep... Oh, dear, that's awful. It's giving me a headache as well. Okay, what you're looking at here, what you're trying not to look at here, possibly, is about 120 vans coming out of a location in Colchester. Each of these bars represents the duration of a van's trip out of its depot. And so the longer bars represent, maybe 10-hour shifts, and the shorter bars maybe represent 4 or 5 hour shifts, something like that. And they're each doing their own thing. They're leaving their depot, they're driving around their area, and then returning back to base. That's a bit more pleasant, I hope. No, it's not. But if I show you the right-hand side, you can get a feel for what's going on. So we've got at the top there, you can see on the right-hand side, you've got a van registration, you've got a route ID, and you've got a time of departure 5:09, the time it returns 5:34. Then the departure at 5:10, 5:11, 5:12, 5:13. Well, that's better. Yeah. Okay, and so on. So what's interesting about this, when we looked at this is just straight off the telemetry devices on the vans. What's interesting about this is, A, how very even the departure stagger is on the vans. So they really are trying to push out these vans as quickly as they possibly can. And then B, the variation in the size of those bars, the length of those duties, is enormous. So would it not be possible to look ahead to try and anticipate the length of some of these bars, some of these shifts, and to be able to say, well, actually, you can have a couple of shifts on one van and leave one van parked. And if we can show that you can do that consecutively for weeks, months, and so on, then I think it's reasonable to suggest you could probably do without 1 or 2 vans. However, here is the tool which suggests which shifts and duties you should be putting on the same van, not you work out what those duties should be yourself. So, and if this is as flickery, I won't keep it on the screen for long. Okay. So a bit of optimization later, and we can start to look at these durations. We can start to we can replicate the departure pattern from the DO. It turns out that the postal workers, the postmen and women, are running their own objective function when they're executing their daily duties, which is to basically get out of the depot as quickly as possible and return as quickly as possible and then go home. And that's what they do. That's their objective. And it's really important. Right, I'm going to stop that because that's horrible. You get the idea. It's really important to understand what other people are doing, because pretty much all the time, even if people don't know it, they're executing some kind of objective. whether it's teaching yourselves about data science because you're enjoying that, or whether it's getting the hell out of here because you're not. And I think it's important because one of the things, the next thing that happens after you ask people to change the way they behave is that they will either go, yes, that's great because that coincides beautifully with what I wanted to do, and it was quite an intelligent thing, and that's what I've been saying all along. Or alternatively, and possibly more often, they'll say, no, because that completely conflicts with what I wanted to do, and I've set up my life to depart at 10 minutes past 5 in the morning and be back at home by midday, and I go and collect my children and all kinds of stuff. So the challenge you have is to try to discover all of the constraints which are going to have the potential to impact on a system like this. And I think what I'm going to argue, just the last bit of the talk, is to say that a lot of what we do has a huge impact on individual people, and sometimes it's a more drastic impact than we might possibly realize, and it's just as important to take into account the constraints that those individuals have as first-class constraints in your system. Because actually, if I'd run that optimization to its end state, we were saving 40 vans, not just 2. Well, if we save 35 vans and we're able to accommodate all of the key people constraints in that model, the company's not going to mind. They're delighted that they save 35 vans. And if we can make the people who work in the DOs happy because we didn't actually push it to 40, then it's actually going to be a system which takes, a system which works. Whereas if you pushed it to 40, it would probably stress the people working with it so much that they would just reject the whole thing and go back to what they were doing previously. Okay, I'm very nearly done. There's tons more to do. That big corporate function could just as easily be an AI-learned, machine-learned function. It doesn't have to be a piece of code, but we're interested as a group in all kinds of techniques and technologies, from optimization and game theory, stochastic robustness and scheduling, time series forecasts. All of these things are elements of your toolkit you will need and will be worth developing if you're coming into this, or if you're working in this field and you're used to that. We work with loads of companies. I run the academic liaison program for the group. We work with loads of universities as well. So Southampton and Lancaster and Imperial College. We work with all of these places, and I'm sure we'll work with many more, to get some of these approaches off the ground. One of the key ones we're about to embark on with King's College is a AI validation and verification exercise, which allows you to try to make robust claims about your AI module before you deploy it. As a data scientist, it's loads of fun to be able to play around with some of these fantastic tools and new tech ideas, but then you have to face the reality of installing them in an industrial system where the people are very keen on being able to test it, being able to reproduce it, being able for it to run within 0.8 of a second every time they press the button. And sometimes these techniques don't quite mold themselves to that approach. So being able to have a reasoning framework around some of these neural net or deep learning activities would be very, very interesting. So we're looking forward to doing more with that. So I'm just going to finish with the last couple of statements, which is this, which, there are some companies which are further down the route than this, than maybe we are, and I completely accept that. The companies are very used to asking individuals to work within the constraints imposed by that company because it's what they've always done. But I think increasingly, companies will have to optimize their operation, not just around their own customers' demand, but also around their employees' demands, because otherwise people will just stop working for them. And as I said, 200,000 people, there's quite a lot of people to accommodate, but I don't see we shouldn't be able to do that in the fullness of time. Good, thank you very much. Quiet audience. Go on, you know when to. Yes, all right, well done.
When you set up the data science engine and stuff like this,
Yeah.
is that with these functions using people who have done before, or a brand new thing from scratch that in some sense is completely
That's a great question. So, yeah, sometimes well. So the question is, how do you, as a new data science group, sort of almost insurgent data science group in a big company? Of course, people wrote forecasts before, and it would be foolish to wander in and just go, that's not working. We're doing something completely different. But the way you do it, first of all, just finding out where these forecasts come from is a big challenge in the first place. And then liaising with them, understanding what they do so that you can sell to them the idea that actually, a 5% improvement in the forecast quality might be a dramatic improvement in the cost saving down the road for the business. It can be a good way of doing that. So you don't try and replace them. You say, well, how about we work on this bit with you and improve this bit of the forecast, and then we can broaden that out to another bit and so on. until you're in a good place. Sometimes you find in a company that the people running the forecast so hate the fact that they're having to do such a manual activity that they just go, oh good, you have it. And they're gone, and then you have to do it. And that happened to us. So, so sometimes you end up working with and trying to help them, and you know, they are the domain experts in terms of a lot of background information behind what they do, and you've got to respect that because they will help seed your initial development and guide you to hopefully avoid pitfalls along the way. A lot of what Maxime talked about rang a huge number of bells in terms of, you know, there's a lot of art in creating some of these forecasting models, and you know, actually humans do have quite a lot to say about how they're stitched together. And then sometimes you come across people where they really don't like the fact they've been given this extra job to do. They'd much rather get on with the job they really were hired to do, and therefore they just give you the thing that you do. So in that case, you can just go, great, we'll just automate that because you didn't want it. And in some cases you go, well, here's some tools, here's some more tools, here's some more tools. And you get it better and better and hopefully keep working with them. But making that relationship work in the first place and then making the tools sustainable and you know, updated in a clean way so that they don't fall over and they can be relied upon is in as much a challenge as anything, because that's a whole different part of the development life cycle than just the data science bit that went at the beginning. Good question, though. Hi, yeah. So we're at trial with that. We're going into a DO, and we are sort of selling the idea of how about we move these vehicles, and we're discovering, as a result of developing a really rudimentary, and apologies for the flickery, prototype like that, we're discovering all kinds of other constraints. And to be honest, what you're doing is you're pushing a simpler model as possible initially, because you know you won't get all the constraints in one go, and you're using that as a discovery mechanism for a lot of the other constraints, some of which won't be desperately important. You're going to go, we're going to park that for another day, but a few of which are really critical, and you've got to get those in. And then you can put, once you really have a core set, handle on those constraints, then you can put some effort into the optimization approach you're using to give an output which is acceptable at the operation level and at the business level. But yeah, we're at that demo deployment, not quite deployment stage, at the trial stage. So yeah, it'll be interesting to see how it goes from here. Cool. Oh, sorry. Okay, hi. For sure. Are we using machine learning or data science to tackle the traveling salesman problem? Absolutely. So I think I sort of feel sort of responsible for the fact that that Royal Mail should be or should be gaining expertise in how to solve TSP, and which is traveling salesman problem, and VRP, which is sort of its big brother, the vehicle routing problem, where you've got many parcels that are going to be separated onto many vans and then pushed out on optimal routes. Indeed, so but they're related for sure. Yes, so we're working with on optimization heuristics. Optimization heuristics is a really fascinating subject. It's one of the few subjects from academia I've seen where the improvement year on year is of order 1 to 1.5% a year in terms of the benefit that it's getting measurably against the objective function you're improving upon, so distance traveled or time executed or something like that. And that's been going on since about the year 2000. So it's really dramatic improvements. And it means that you know, it's one of those areas where it's worth your while, your data science group, getting their hands dirty and implementing some of these, in some cases, quite simple algorithms directly, rather than going out and buying a third-party package, which is probably using a bit of technology that's 5 years old, because they can make a real difference with that and they can make some real impact. So yes, we're doing that for it doesn't work so much on the walked routes because they are the same every day. And they have to go down every road and all the rest of it. But it works very well on these ad hoc deliveries of parcels where you've got 10 locations, 20 locations, and you need to deliver to those. Sorry? Ad hoc deliveries, where you don't know, if you know that you're going to visit most of the houses in a street, up one side and down another. You just walk up one side and down the other. And there's ways of stitching the streets together so that works. But where you've just got 20 parcels that are coming from, or 200 parcels that are coming from a geographic area, and it's a different 200 every day, then you do that. And that's what we're working on. And yeah, so that's very, very exciting. And some good large neighborhood search is definitely something to look up if you're interested in that. Cool. Yeah. Hello.
So in the talk you spoke about non-static time series. Now, I think it's a challenge here when you look down rather than king and being right. Is that quite hard to balance that? Balance the time between developing your technologies and building new?
Oh, yes, that's a terrific question. So how do you cope with a situation where you build a tool and it works now, and then 5 months later it stops working for some reason? Well, for sure, you have to own what you do, and you have to be approachable for people to come back to you, and it may be that it triggers a whole new investigation to find out what the new ground truth is. There are certain things you can do for mitigation. I'd be interested to, we're working with University of Lancaster on change points in time series, which look for unexplained changes in time series, and it's not just mean change, it could be variance, it could be skewness, it could be all kinds of properties in the time series which suddenly change, and you've got no idea why. Often in a big company, stuff changes all the time and nobody tells you, or you're the last person to know. So if you can, if not anticipate those changes, at least make sure you observe them as quickly as you can and factor them into your forecast, then that can make a huge difference. So it may be that you're a bit, the operation's a bit wonky for a day or two, but then suddenly it recognizes it's a change point has happened, and it can then recalibrate its forecast and go ahead from there. That's sort of the slightly get-out reply to that. But then, yes, I mean, how you respond to something changing so dramatically that you basically have to go in and re-engineer, well, that may be what you have to do in the end. And it's important that there's a good sort of tool chain pointer which allows people to say, yes, it was you that developed this, and we need this to get fixed, because otherwise these things can get lost in the midst of big organizations, unfortunately. Yeah, cool. Thank you very much.
You've got obviously financial data which has been used. Now that we have that, I think this is a really powerful abstraction, and with the right set of data and would like to predict in the future